From the Southern Studios of Way Happy, this is Mr. Meyer, and I am welcoming you to the prerequisite chapter, P1. Good job finding this video. You will see as it goes along. You can take some notes. You can scribble on the ones I put up on the website. You choose how you want to do it, and it will probably pause and ask you a question here or there. And just sit back, relax, and let's see what we can get through some of this stuff that hopefully feels pretty familiar, but we want to make sure it is still in your brains after all of that summer time off. Now this one, piece of cake. Things you're going to learn: real numbers, interval notation, which is real important, and you want to make sure you get that. And then just exponents, and if I get to it, scientific notation, or you can look it back up in the book if you're not too sure what that is. But let me know if it scares you, and I will show it to you in class. Real numbers. Real numbers are just numbers that helped the world talk about things. You wanted to know how many years you were alive, and you were telling your caveman friends, you'd have to give them a number, right? We had to have something that would make sense that we could tell other people. Otherwise, it got really weird. And so numbers came into our lives. We counted things. They represented so many valuable tools that we have to use. So therefore, we use real numbers. Now, real numbers are things that are the natural numbers, like the ones you use when you count. 1, 2, 3, 4, 5. They're also the whole numbers. Add 0 to that list. Those are called whole numbers. So adding a 0 just changes it from natural numbers to whole numbers. You also have integers. Integers are all the whole numbers, but it's also the negative ones. So integers probably are most common. Students and everyone likes integers, right? They like a nice, pretty number. But real numbers can be more than that. They can be numbers that are written as a ratio, right? So right here, you see in the middle of the page, you see this little ratio. That is also a real number. As long as you can write it as a fraction, that's pretty solid. Just make sure that your denominator is not 0, because horrible things happen when that's the case. You can write decimal numbers. A lot of us don't really like decimals, but you could write them, and they are real numbers if they at least terminate, meaning the decimal stops at some point, or it repeats itself. And remember when you always wrote that as like a little bar? You were like 3.672 with the 2 repeating forever and ever and ever. So that meant that it's a real number. If for some case, the number like pi or Euler's number, that so far we've never been able to find it to repeat anywhere, those are not real numbers, right? Those are not rational numbers. Those are called irrational numbers. They are still real, but they are called irrational. So irrational is the ones that I can't write as a fraction because they don't ever terminate and they don't ever repeat. And then let's talk about inequalities. Now, lots of you love your inequalities. They're super important in math because sometimes we have an answer that isn't like x is 5. It's everything bigger than 5, right? What are the ages of the kids in the classroom? Well, we could kind of try to go, say you wanted it in days. Oh my gosh, that'd be crazy. We'd say years and days or whatever. But maybe I just want to say, hey, they're all over 10, just to be safe. And so their ages are over 10. That gives me a whole range of ages. Or maybe I'll say they're all between 10 and 20. So therefore, at least you got a little narrowed range of where they are. That's what we have when we talk about inequalities. We talk about a range. And when you're a bounded range, then I say stuff like, all the numbers between, all the numbers between 3 and 12, right? That's a bounded range. I'm saying that there are people, or whatever we're counting, let's say we're counting Oreo cookies in a jar. I'm saying there's 3, and there could be 3 with that little line underneath says that there's 3 or 4 or 5 or 6 or 7 all the way up to 12. In fact, I'm actually, with this notation, I'm saying there's also decimal versions like 3.7 and 3.28 and 4.91. But for sake of argument, if we're talking about Oreos, let's just talk about integers. So that is how you would say an inequality that you're used to. And hopefully you've maybe even been introduced to interval notation, which makes things prettier. And it just goes like this. It says, all right, if you're going to talk about the numbers from 3 to 12, you start with 3 and you go all the way to 12, smaller number always on the left, bigger number on the right. And if that number that we're talking about is included, I want you to use a bracket. And if it's not included, then I want you to use a parenthesis. So since both the 3 and the 12 are included, I'm going to put brackets around it. And that says the exact same thing as this, right? They say exactly the same thing. That says start at 3 and go to 12, include both of those numbers. I could change it a little bit different. Maybe I should show you a visual on a number line, right? Here's the number 3, and here's the number 12, and we're saying 3 all the way to 12 is included. Now, what if I want to say, some parts, like let's say the number of Oreo cookies, some have been eaten. So I know there's more than one, I just don't know how many are more than one, and it's less than or equal to 7. So now it's between like 1 and 7 cookies. What would that graph look like? Well, at the 1 you'd have an open circle, and at the 7 you'd have a filled in circle, and it would be everything in between there. So we use a line up, didn't want to do that. We would use kind of a darker line in between. And how would I do that in interval notation? Well, again, you're bounded. You definitely have a starting and ending. You're going from 1 to 7. That's how I know it's bounded. But the 1, I can't include it. I know there's more than 1, but there's not exactly 1. So I'm not going to include it. But I will include the 7 because there could be 7 cookies, and I know there's between 1 to 7 cookies in there. That's interval notation. You want to get really used to interval notation because we're just going to use it all the time, and it's super helpful. Remember, parentheses mean that we don't include the number, and brackets mean we do. So this is where I get to ask you one of those really exciting questions, and we'll see how you do, and I'll see you in a few. Wow, what very nice work you did for your first video. Loved it. Keep up the good work. Now what about unbounded? Unbounded is when you don't have an endpoint on one of the sides. So you're like, earlier I said everybody in the room is older than 10, right? That's unbounded because I said 10, but I never stopped anywhere, so there was never an end. And so how would you write that in math? You would say, well, you go, all the x's are greater than, let's say we included 10-year-olds. Everyone's greater than or equal to 10. That's really easy with an inequality. Also, here it is on a number line, right? You would have 10, you would have it filled in, and you would say everybody's bigger than that. Well, let's talk about interval notation. The way I do that is I say, hey, you start at 10 and you go all the way to infinity. And now you decide if you're bracketed or not. Well, the 10 was filled in, so that's going to have a bracket saying we're going to include 10. Now, infinity is not really a number, it's a concept, and since I can't include it in the numbers, I'm going to put a parenthesis saying it's a really big number. In fact, you will notice that infinity and negative infinity will always have a parenthesis. They will never not have a parenthesis. And so this is what we say for when we want it to go on forever and ever. So that is your unbounded intervals. All right, let's try a couple examples just for fun. You can see that this is a bounded one, definitely bounded. It goes from -3 to 4. So if you're somebody who likes number lines like I do, I love number lines. I think they help me visualize things very well. I know it goes from -3 to 4. It includes the -3. It doesn't include the 4. And it's all of this shaded region here. Now, what would that look like in interval notation? Well, I go from -3 all the way to 4. And all I have to do now is say this one's bracketed because it included the -3. This one's parenthesed because it doesn't include it. It goes all the way up to 3.99999 infinitely, right? So that's it written. How do you write x is greater than 4? Well, again, number line, if you like. Here's the 4, open circle, everything bigger than that. And so now how am I going to write that? I'm going to write 4 to infinity. I'm going to not include the 4. I'm going to not include the infinity. And that means all the numbers. Now, just as I'm writing this, I'm thinking, sometimes you get those weird ones like, let me merge these two together, right? What if it was from -3 to 4 and bigger than 4? Right? So you have something really crazy like this. Well, the way we write that is we write, well, same exact thing. You're going to go from -3 to 4, and then you're going to go from 4 to infinity, and you just need a little symbol in between, and it's called a U. It's a little U for union. So you're going to say that it's this stuff and it's this stuff. And that's how you would write that inequality if there were more than one part. You could have 10 parts, and so you'd have to write them all with a little u in between saying these two things are happening, all of this and all of this. Just thought I'd throw that in because it does come up. All right. Then there's this thing called exponents. You've probably dealt with exponents forever. It's going to be very important when we talk about logs. So make sure you understand the parts of an exponent, right? Or I should say a power. The entire thing, like x to the third, that thing's called a power, right? But it has two important parts. It has a base and it has an exponent. And though that vocab is just so we can talk about different parts of powers and all their properties. And so make sure you understand which one's the base. Make sure you understand which one's the exponent. Make sure you know what it means. That means an x multiplied by itself 3 times. Probably nothing that's blowing your mind, but at least something we can talk about. Look at all those properties. They are insane, right? There is, a ton of different properties that you've worked with and dealt with and probably love. I can tell you the ones that I know from past that kind of scare people are anything to the 0 power is one. That usually gets a little tricky. Negative exponents, gets a little tricky. That just means if I'm in the numerator, move me to the denominator and get rid of my negative sign. If I'm in the denominator, move me to the numerator and get rid of my negative sign. Works out really well. You can distribute exponents. You can multiply them back together. You can, if it's a fraction, you can give it to both of them. So a lot of neat things. A lot of neat orders that you could do them in. So you want to do it in what's comfortable for you. So that's why I grabbed 3 quick examples. Let's look at A right there. So the rule there is these are all multiplied together. In fact, this is one big multiplied mess. Do you see that? Do you see that in math we could have written this as 2 times a times b cubed times 5 times a squared times b to the 5th? There's no distribution property because there's no plus or minus messing it all up. This is just all multiplied together, and somebody chose to put parentheses where they did, but they didn't need to. It's all just multiplied together. Just one big gobbledygook number. And so you can rewrite the order if you'd like. You could change this to, maybe I want the 5 up by the 2, so at least I could multiply the numbers together, and then maybe I'll get the A's together and the B's. Only doable because of all the multiplication. There's no adding or subtracting because that's the big fit in math now that you're older, right? So here I'll rewrite it, but it'll be 2 times 5 times a and a squared times b cubed and b to the 5th, so there they all are. If I pretty this up, it's 10. Now here's one of those properties. They have the same base, so add their exponents, a cubed. They have the same base, b, add their exponents, which is 8. And there is my answer for A. And I'm feeling very good, right? Let's talk about B. B would be something like, look at that, u squared v to the negative 2, and then u to the negative 1, v to the 3rd. I see 2 things you could do. You could definitely subtract exponents, which is a great choice, and probably the quicker way. You could also just move things. So I'm going to do it both ways. Let me subtract exponents first. So this is a 2 minus a negative 1. So that's u, and then 2 minus negative 1, which would be u cubed. And this would be v, a negative 2 minus a 3. Oops, I forgot to put my minus in there. That looks like multiplication. Sorry. Here, I'm going to erase that because I don't want anybody crying about that later. Negative 2 minus a 3. So what do we get? We get u to the 3rd, v to the negative 5. And what does that mean? That means a u on top and a v on the bottom because he wants to be moved. And now he's v to the 5th. Done, right? Or, like I said, you could have done it a different way. You could have said, hey, look, you got a u squared, and the v to the negative 2, I want to move down, so it's a v to the 2 on the bottom when I moved it. The u to the negative 1, he wants to move up, so he's going to come up here, and that v cubed is positive, so he's going to stay right where he is. So it would look like that. And then what would you get? Well, you got same base, add their exponents, so u cubed, and same base, add their exponents, v to the 5th. Oh my gosh, crazy. They're the same. Of course they're the same, right? That's what's so cool. You could probably find another way to do it. I gotta love this stuff. You really gotta love this stuff. All right, what about C? Not much. Usually I would try to reduce stuff in the fraction first inside the parentheses, because parentheses are always like, ooh, do whatever's in there first, right? Unfortunately, not much to do. I can't reduce the 2. The 2's don't cancel, right? That's x times x. Doesn't do me any good. So the only thing left to know here is this one property that says, hey, you can distribute that exponent, the one on the outside, to everybody. So that would be like x squared to the negative 3 and 2 to the negative 3. Now you just figure out what the heck that means. Well, one thing like we saw last time, you could move these guys. So since this x squared has a negative 3 exponent, it's actually going to move to the bottom and have a positive exponent now. And look at that poor 2. He's got to move to the top and have an exponent. So what am I left with? Well, 2 cubed, 2 times 2 times 2, that's 6. Haha, just kidding, it's 8. And x, ooh, look at this property. Right about, where is that property? Where is she? Right here. All right, number 6. If you have 2 exponents, you multiply them together. So that is x to the 6th power. And there is my answer, right? Would it be bad if you wrote it as 8x to the negative 6? No, not really. It wouldn't be bad. Just another way to write it. And there's nothing wrong with that. The only thing is usually they'll tell you no negative exponents. So that's why it would be written the way I boxed it. But it's not wrong the other way, unless somebody said that. And that's the big Common Core thing, like, oh my gosh, would you know that that's the same answer? Yeah, right? Once I'm comfortable with exponents, I know exactly that's the same answer, and I'm feeling pretty darn good. And I hope you are too. That's it. You survived, right? So we'll practice some of this stuff in class. You have a great day.